uncertainty and logic. And we have a very light program this afternoon. So Cassio will entertain us, and then at 3 we have a reception where we can all chat. So we have all the attention for this one talk. Go for it. Thank you.
Thank you all for being here. I will talk about the Credal models. So this talk, it's an attempt to convince you that we may do well if we use more than probability. So let me start with 12 years ago. So this is an XKCD cartoon about chatbots. And, well, it was making joke about that, right? And, well, nowadays we are using, or many of our students and others are using ChatGPT with great success in a number of tasks. I'm not going to claim in all tasks, but I would claim at least that the joke is a bit outdated. And the reason, well, one of the reasons for that is that we got more and more data and more computing power. You don't have to try to read this graph, but it's just showing how faster we got in terms of computing, and also it's clear that it got much cheaper. To the point that about a year or 2 years ago, I was asked to talk about deepfakes, and then I said I would try to do it. I mean, I have no idea how to do this. I had never used any tools for that. And then I went online, and I found some tools that used generative adversarial nets, and you could plug a video there, and they, crush the numbers and whatever. I had no idea what the thing was doing. And without much effort, and within an hour, it's not amazing, but I managed to put the face of the then, well, still Prime Minister, and the face of the then Health Minister when they were giving one of the press conferences that was related to COVID. And yes, I got very surprised at where we are with AI. But more recently, and this is just a month ago or about so, if you follow some of the news outlets, you're going to see things like Game of Thrones author suing ChatGPT. You're going to see Google being sued because of directing motorists to a place that there is no bridge for more than, I don't know, 8 years or 10 years, something like that. So things have changed in AI. There are many consequences of that. So the research has grown very fast with impacting society, many applications, many people using this. And many people claiming that there is need for regulation of AI and the research in AI, certification and investment. You're going to see here a joke of AI trying to help itself. I will go further. So this is now a bit more than a month ago. If you look on BBC News, then you would see a news article with a few comments inside, and I will quickly read the comments. Congress should engage with AI to support innovation safeguards. That was Zuckerberg from Meta. And then I think if this technology goes wrong, it can go quite wrong. We want to be vocal about that. That's Altman from OpenAI, the ChatGPT. We want to work with the government to prevent that from happening. And I think there should be a regulatory body established for overseeing AI to make sure that it does not present a danger to the public. That is Musk from SpaceX, Tesla, and so. And he continues, better that the standard is set by American companies that can work with government to shape these models on important issues. I'm not going to dive into discussing this, but I think that, I'm a person in university, and I think we should be involved on this. And one way of being involved is maybe to try to make steps on AI and models that give us more trust on what is going on. So I brought a few examples for us. I hope that the examples clarify a few points in my selling of this something more than probability thing that will become clear later. So let's say you have a patient, Mr. Sick, that either has an autoimmune disease or an infection, and without treatment, he will likely die very soon. If you don't know, the treatment for one of these diseases typically kill you if you have the other, and vice versa. And assume the diseases are equally likely. It's a fake example. Let's say that after studying this case in private, the doctor Imprecision tells she does not know whether it's A or B, which one of the two diseases, while Dr. Precise tells it's A. So which doctor you would prefer if you were Mr. Sick? I will not ask you to answer the questions, because I'm getting every time disappointed when I use this example, and I don't want to get disappointed with you. I would tell my answer, and my answer would be probably I would be more impressed by Dr. Precise, because it told me something. The other just said I don't know. But let's now switch to looking inside. Let's, in this hypothetical example, think the following. Dr. Imprecise concluded that she doesn't know by studying the data, carefully analyzing everything, and then she said, I cannot get to a conclusion. And let's say Dr. Precise gave an answer A after flipping a coin. Now I'm very sure about which one I prefer. I prefer the Dr. Imprecise, even if I still do not know which one is my disease, but I have this knowledge, so I can work further on it, trying to find more advice and so on. Let me go for another example about knowing when we don't know. So let's say that we have a typical task of classifying digits. So you're giving images, and you have to guess what's the number in the image. What is best? So it's best an approach, an AI approach, that always predicts a digit and gives you an accuracy of, let's say, 90%? Or is better an approach that predicts an image, a digit, with accuracy 99.9, but sometimes it says I don't know? Obviously, assuming that this I don't know does not happen too often, because otherwise then you don't have so much information. Or even another approach, which sometimes predicts multiple digits. So it says to you it's a 6 or an 8, but nothing else, with an accuracy of 99.99%. And there is no, I don't think there is a correct answer here, but it really depends on the task that you have and the type of risk that you are dealing with. Let's go one example further here. Let's say that BBC is paying us to discover the popularity of EastEnders. It's a long-running soap opera. And we decide to call 10 random valid phone numbers. And 4 people answered the phone and said they like EastEnders. 1 answered the phone and said they do not like EastEnders. And 5 did not answer the phone. So a typical AI approach. You got 5 answers, 80% like EastEnders. Is that okay to just report that to BBC as the conclusion? Let's just have a quick thought about here, right? So there's something missing that we didn't use. So EastEnders is, I think, more popular among older. Maybe you may argue that's not the case, but it seems to be the case. And young people typically does not answer the phone. So I think that would already maybe change our impression and how we have to deal with those 5 cases that did not answer the phone. So I think that we can do a few things to improve AI. So there are many desirable properties. And those examples, they touch on some of these points in interpretability, robustness, including to missing information, the explainability of what you're doing, privacy awareness, and fairness. But they usually this costs something. And my question is if we're willing to pay this price for something. So this is my justification that, we should think very well about improving AI in the best possible way. And I will talk about the probabilistic view of this. So there are at least 3 different levels of knowledge that we could encode. The first here, let's first take this example as being a football match between Italy and Sweden. And we are interested in the outcome for Italy, which can be a win, a draw, or a loss. So let's say that we know that Buffon, that is Italy goalkeeper, is unbeatable, and Sweden always gets at least a goal against them. So in this case, we are certain Italy wins. So we can represent this with a probability of win equal to 1 and 0 for the other two possible outcomes. But you may be a bit more uncertain. You may say win is twice, so 2 times more probable than a draw. And this is 3 times more probable than a loss. And you can, again, represent this with a probability mass function, 0.6, 0.3, 0.1 in this case. And you can go even a step further. Which is this step further? Well, you could just say that win is more probable than a draw, and this is more probable than a loss. So you're not really specifying one probability, but you're specifying constraints on probabilities. So you could write down these as constraints as we have here. I will argue that this imprecision is quite useful, but before I go there, I will show a bit of circuit, because I will enhance that circuit with you towards that type of imprecision. So let's open this parenthesis so that I can talk about first the probabilistic case, but the precise probabilistic case. So folks have been working on what was called sum product networks 12 years ago, and you may hear this as probabilistic circuits here. There is a bit of confusion in terminology, but I will use here some product networks to make it clear the restrictions I'm using on it. So in this case, we have a model that is something between the neural networks one side, which are circuits, and the Bayesian networks on the other side that are graphs that you can interpret as with a Markov condition. These circuits are somehow in between, and they represent complex mixtures of distributions. One distribution, multivariate. In this example here, you have a distribution over 2 Boolean variables A and B. The circuit is a graph. We have different types of nodes. So we have here indicator functions. I'm only use binary random variables here to make the exposition simpler, but it's not a limitation. You have weighted sums. So the sum nodes are weighted sums of the children of them in this DAG, in this directly cyclic graph. And you have product nodes, which are product of the children. And we use a few extra constraints in this sum product networks. So the product nodes multiply variables that are a partition of the variables that it had in that case. So that's why you see x and y on one side and z and w on the other side. So it has to be a partition. And the sum nodes are over the same variables. That's why you see p of xy, and then you see p of xy in the children. And that is what you also see in the graph here. One great advantage of this type of circuit is that it's representing a joint distribution for the variables, in this case a and b. And you can compute marginals and conditions very efficiently. So if you want to do inference, in this example here, you want to compute the p of a equal to true, all you have to do is to put 0 on what is against what you want to compute. So you put a 0 on the leaf that has not a. You put a 1 on the rest, and you propagate computing products and weighted sums. And you get the marginal probability of a there on top. So you can do marginal probabilities very efficient. You can do condition very efficient. You can then work with this distribution to do decision-making, classification, and model your domain. There is, yes?
Connection of this to the trees, the circuits we have seen before from Michael Monet.
They are the same as many other models. I mean, there are semantic difference in some cases. Some others a bit syntactic difference. We can discuss more on these details because it depends on the assumptions you use inside the structure. We could talk a bit more about, but yeah, they are very similar. Here there is another example, actually. They are very similar to decision trees. So if you take a decision tree that you see on the left, you can easily write it as a probabilistic circuit. What you see in the right, in the picture here. And well, this connection is very nice because automatically you get a generative model out of a decision tree or a random forest. And you can use this as your machine learning model. So in the case of these generative random forests, since random forests are the state of the art for tabular data, this translation keeps us with the same results, the same state of the art results for tabular data, but you get tractable marginals. So you manage now to work with missing data. So you can compute probability of your class giving evidence that does not need to be complete. You can use the probability of your observation, for instance, to try to do outlier detection. You can use smooth values on leaf nodes to make the boundaries of your decision smoother and not just as a decision tree, which are sharp partition of your space. You can do robustness, and we are going to do a bit of that in sensitivity analysis. So interpreting these random forests as circuits give you a few benefits. You still have one probability distribution, but you can do a few cool things with that. So you can use P of X to try to know when you don't know. So if you look there to the left, you are going to see the cases that have a low P of X, and in red, when you got right or wrong when you try to classify those images. On top is the MNIST, and the bottom is the fashion MNIST. And if you look to the right side, you're going to see the case where P of X was high. So you have a very high probability of the observation. And in those cases, you see lots of green, right? But also you do see not so much variation on those. But it's a benefit. So already a benefit of having P of X, what you can use to try to understand if you're doing a good job or not, a measure of quality of your classification results. You could use for outlier detection. So it's also a common data set on wine. On the left, you're going to see the data trained with white wine, and then you see the P of X for both white and red wine. And you see that there is a better separation on the bottom, where we're looking the P of X, instead of looking to the marginal probability of the class given X, which is all you can do if you don't have the P of X in a generative model. And the same on the other side, but inverting, trained with red wine, and then you see how they split red and white wine. But P of X has limitations too. So imagine a case that you have badly written 5s and 6, but you have many of them. So you have many 5s, many 6. So it could be that P of X for those are quite high, but still there is lots of uncertainty between 5 and 6. So we could try to do a step forward here beyond P of X. And I will argue for this sets of probability distribution. So this is a Credal set, the definition of Credal set. First, in our example there, we had the determinism. That was one probability, was a 1 for one of the outcomes and 0 for all the others. We can use single probabilities. So each one of the blue points is one probability distribution. One is 0.4.6, the other is 0.7.3. Or you can use as your model to represent your knowledge a set, in this case an interval between those points, so the blue line here. So the Credal sets are basically a geometric entity in high dimension, a polytope. We usually assume them to be convex, and they give us more power in representing, because, well, a point is also a Credal set, but you can use a set instead of using a single point to represent your knowledge. So you start with one point, it's a singleton, but it is a Credal set, but you could use any kind of polytope you want there. And one of the key advantages, for instance, is to model ignorance. So if you just take a uniform distribution, usually this means that you like all the outcomes equally. It doesn't mean that you don't know anything. So you could better use your whole simplex, so all the probability distributions that exist as your initial information, as your state of knowledge at that point. So it gives you more flexibility there. And you can also then extend this by putting expert knowledge, such that this probability is greater, of this outcome is greater than the probability of the other outcome, as we did for the example of Italy versus Sweden. And you can go beyond making lots of rules, which typically help you with experts to represent your knowledge by using intervals instead of using just single probability values. With these models, you can go beyond using a single variable and use multiple variables. So in this example here, there are two binary variables. Obviously, the domain of the problem gets higher, so the dimension is higher. This Credal set becomes a more complicated polytope in higher dimension. But all the rules that we are going to use, they work there too. So we can do a mapping between a probability and a set of probabilities. So before we go to that, I have to mention there are things to pay for when you go to sets of distributions. So when you have one probability distribution, we typically define independence of two variables as the marginal probabilities of those variables can be multiplied. So P of X and Y can be factorized as P of X times P of Y. If you have sets, then you have different types of definitions. I can quickly think about two of them to consider, and this is something you have to have in mind when you're working with sets. So one way would be, call it a strong way of defining independence, is to define that you have stochastic independence in each one of the extremes of your set. So the borders of your set, the corners of your set, the extreme points satisfy the pointwise probability independence concept. But there is another called epistemic irrelevance, where actually you say that your set does not change when you observe something. It's a set concept. So it's like you have information about X as a set, and then you observe Y, and the set remains the same set for X. This is way more complicated to deal with, and I will not go there, but I wanted to alert you, we pay something when you want a model that is more expressive. So I'm going to work with the strong independence from now on to show you a few use cases of it. And with a strong independence, yes?
There's also stronger independence where everything in the set has the independence.
There is.
But that's not convex anymore, I guess.
Yes, you have convexity issues, and often what you can work around is by convexifying the sets when you do operations on it. But yes, there are other concepts. We can also talk more about that. Every concept you use, you may end up inducing a different model with that. I will try to stick to, let's say, the one that is closest to sensitivity analysis in precise models, because that's what I'm going to show as a use case in the next slides. But you have a good point. There is called complete independence, and well, you can hear a few other different definitions of independence. So when you go in, yes?
About the intuition about using a set of probabilities is you want to say that you don't know which one is the right one? Is that the intuition?
That's one of the possible interpretations of it. It could be interpreted as I don't have a single one. So it's not that I don't know which one is the correct one. I will say that the world is imprecise. So the correct thing is a set. That would be a little bit different interpretation. I will use in this presentation your exact explanation. I will assume there is a correct one. And I will say that my set is my lack of knowledge of which one is, but it's one of those. So indeed. With this concept, which is the simplest, call it the strong version, simplest in terms of explaining to you, where each point, extreme point, has to satisfy what a probability distribution would satisfy in the precise case, we can do all the typical operations of probability as we would, applying it to each point in the set. So that's all that this slide is telling us. So if you want now to manipulate sets, just repeat your process as you would do in one probability with all the extremes of that, and keep convexifying if needed. I ask you if you are questioning what this convexification is generating and the problems. Let's discuss this later, okay? But it's really not a big deal, as many of the things that we do are actually linear in these high dimension spaces, so the solution will be in an extreme point. So it does not create really big problems. So the basic operations is repeat the same for each one of the points, but you may have many points on this big polytope. So we do have better ways of computing, but I'm not going to go there on how to compute with this. Though you can already see that is more complicated than working with a single one. Obviously, you have many of them. So not necessarily you're going to get algorithms with the same kind of speed that you would if you have a single one. Typical then extension, and I would mention in two. One is extending Bayesian networks to the Credal case. So if you are aware of Bayesian networks, so you have this DAG, directly cyclic graph, with a Markov condition. So every variable is independent of the non-descendants given the parents, which induces a factorization, or you can look this the other way around. You can come from the factorization and induce your definition. But it is a very nice representation and very interpretable representation. Typically, what you associate to the nodes is a conditional distribution for the node, the variable associated to the node, given the parents. In the Credal case, what we do is that we associate a set for the node given the parents. So it's a natural extension of a Bayesian network towards sets. But now you have all these sets in each one of the nodes. So you can see that computations will be way more complicated, because if you want to do variable elimination, you have to consider all the possible stream points and keep multiplying and working with all of those. So there are quite efficient algorithms, not tractable. Don't get me wrong when I say efficient. They are pretty slow, but we can solve many interesting problems. And there are cases where this is even as fast as the precise. So this is an example with numbers, a very well-known little Bayesian network, and you have intervals defining the conditional mass functions instead of numbers for each one of the mass functions. And this has been used, I will not talk much about, but you can ask Alessandro about, because, well, his application. So the Swiss Air Force seems to be very happy with the idea of not taking decisions sometime. But I will leave you with that. But there are really risky cases where having sets of distributions is appreciated more than having a single one. To work with those, though, we have a bit more of a discussion here on how we are going to get to be able to do classification with this. Because if you have sets of probabilities, it could be that some of them tell you that this is a 9 if you do the operations with one of the extreme points, and another one tells that this is a 3. So what do you do with that? Well, a typical thing, or the simplest one, is to compute bounds for, in this example, the probability of win, and the blue represent the bounds, so the maximum and the minimum probability of win, and you do the same for draw and the same for loss. And if the intervals do not overlap, then you can discard those that are under, because they are not the best. You can do better than that, and you can compare not the intervals on the outcomes, but the results for each one of the P's that you have. And if for every P, one of them is better than the other, you can also discard that option and keep the one that always beats the other. And this is what here it's called the maximality criterion. So there are a few different decision criteria when you work with sets, because it's the same as having the opinion of multiple people. And you have to have a decision-making procedure on how to deal with the opinion of all these people, which in this case, the probability distributions that are represented by taking the extreme points of the Credal set. And the second model that I'm going to mention to you is the Credal version of that sum product network, the Credal version of the probabilistic circuit. And naturally, what we do is, instead of putting weights on the sum nodes, we put sets of weights in the sum nodes. So it's a quite natural extension, just as in the case of the Credal Bayesian network, that instead of local conditional distributions, we put sets of local conditional distributions. Here, for the weights, we put sets of weights. In this example, for the values of, I cannot read, for the values of x4, for instance, you have a set there with an interval that goes from 0.54 to 64, and so on. So in this case, you just build it with the intervals you would like. I will build them with a certain way in a moment. I would take a probabilistic circuit, learn it in the way that you like the most. So give me a probabilistic circuit representing a probability distribution. And now I'm going to take every one of the weights that you have there, and I will perturb them a little bit. So this is what this is trying to represent in the picture. So it's called Epsilon contamination. You take your precise distribution and build an interval around it. And this builds to you a Credal version of probabilistic circuit. But which interval? How you define this? Yeah, so I will call epsilon robustness the maximum epsilon that you keep increasing this set until the point that doesn't matter which point you take inside, your decision is the same. So if you start there in the middle and you're saying this is a 9, now I start growing the intervals everywhere up to the point that doesn't matter how I choose P, they all say it's a 9. But there is a moment that's one of them you say, I think it's a 3. Stop exactly at that moment, okay? And that is what I'm going to call the epsilon, as epsilon robustness. If you can grow this a lot, means that even if the parameters of your model would be perturbed quite a lot, you'd still get the same answer. This is done per instance. So you give me an X and you're asking me a Y. What do? I take your circuit. I guess the Y using the circuit. And then I start making that circuit imprecise, Credal, growing until the Y is still the same. Up to that last point, when Y changes depending on the extreme point you choose, I stop. Okay? So now we know what the epsilon is. Then this graph will show you a reasonably monotone set of functions, one for each data set. And on the X, you are going to see the amount of epsilon robustness. And on the Y, you're going to see the accuracy of the model for a certain subset of your data based on the epsilon robustness. I will not try to go to the details of the graph, but the important thing here is that as you are more robust, you also have higher accuracy. And you can compute epsilon robustness without knowing the answer. So you can tell if you're doing a good job or not before really checking if what you guessed is correct. How is this different of P of X? Well, it's different. P of X is a measure of how many things you saw close to that point. This is a measure of how much you can perturb your model, sensitivity analysis, if you will, until your decision changes. So it's a more of an adversarial way of looking to the task. So in this graph, you're going to see on the left side the results with the highest and lowest epsilon robustness. The far left is the lowest, and then the next one is the highest set of highest epsilon robustness. And on the block on the right side, you're going to see the P of X that we had seen before. Okay, I just copied here. So if you take a look, there is more variability. So they are different. The epsilon robustness, when it is right, is not like lots of ones, like you see on the P of X. And I'm not going to claim which one is better here. I think that goes maybe beyond the amount of time I have. But I'm going to claim that this epsilon robustness is a pretty interesting way of analyzing if the thing that you are guessing when you do classification would change if you had learned the model with a slight variation, a slight change on your model. So this is the use for robust classification, which at some point got quite interesting results.
Is it obvious that you can even compute this epsilon because there's so many points?
Yes. It's not obvious that you can compute that for any type of model, but for the Credal probabilistic circuits, you can do that in linear time for a given epsilon, and you can do bisection to find your epsilon. So, well, you actually pick an epsilon. This induces a Credal set. You can compute in linear time if you have a single answer or not. I cannot explain how that quickly, but basically you can propagate maxes and means because that's what matters. You can compute efficiently the result of expectation of functions, even with negative values. So you do that computation, and you can say there is more than an answer here, or all the p's agree. You can do that in linear time. And then the epsilon, you have to have fixed for that to be in linear time, or you have to propagation a function of epsilon. But the solution to that is to do bisection on the epsilon later on, which gives you a precision very quickly. So if you run that 5 times, you already have a quite good idea where the epsilon is. But we can discuss later on how I do this that efficiently. But it is same complexity as the precise probabilistic circuit, this computation. So every time you propagate, when you do products, you just, if you want maxes of maxes, you do maxes And if you do sums, you just solve a very small continuous knapsack problem, if you have intervals. Or if you want more general, it's a linear programming, it's a small linear programming problem that's there in the more general case. But if you have intervals, it's a very tiny continuous knapsack problem. So the algorithm is really, really fast to run this, as fast as the PCs. Indeed, this is a key benefit of that. So we can compute this Epsilon quite quickly. This is actually quite old, but I wanted to show because it gives us a quite nice intuition on what the model is discovering by sensitivity analysis. So if you look to the first row there, those are people who are forcing a surprise phase. And if you look to that graph, surprise is the easiest. So on the X there, you have the Epsilon robustness. And it's way more robust for surprise when you compare that to anger and disgust, which are the two last lines. And arguably, it's quite hard to discover the difference between the two last lines here. But the one there on top is very clearly different. So this was a nice thing, and that we got with the Epsilon robustness. So this was my attempt to sell you sets of probability distributions. There is lots of ongoing research on this. There is a quite strong relation with causal inferences that I believe you are going to hear about in a few days. We are doing Credal circuits for portfolio optimization and a couple of other topics in finance. We're doing Credal clustering. Very soon, we're going to have some interesting results related to the steps that you have inside a neural network as Credal clustering. We are trying to use this to combine this probabilistic logic and deep models using Credal sets. And this is the topic that I'm going to spend my last slide on, is the third bullet here, to tell you why this is quite interesting. But I don't have the final result here. So I would call this unpublished work, an invitation to join. If you think about probabilistic propositional logic, let's go simple on that. Say, you tell me the probability of A or B, it's equal to 0.3. So you tell me a probability of a probabilistic logic formula. We can easily encode this in a type of Bayesian network with putting evidence there. We could do this forcing bounded tree width, so forcing that network not to be too dense. And we could do structured learning with those variables. This can be compiled into a probabilistic circuit to make it computations quite efficient. There are some 5 steps I jumped here already. You actually have to invert some nodes to be able to put this constraint there. There are a few intricacies, but the overall idea here is that you get a circuit and then you can train this. So one of the nice things of circuit also, you're training the parameters directly on the circuit. So just as parameters of a neural network are trained, and this usually gives you a boost on quality of your model. And by doing a procedure like that, you get sort of a neuro-symbolic AI direction. We are trying this via transformations. We are trying currently this directly on circuits. And we can discuss a few different ways of trying to put them together. I'm not going to go to all the details, but I wanted to emphasize why the Credal version is so essential. Actually, without the Credal version, we cannot do these steps. And the reason why it's so essential, the Credal version, is that if you tell me that the probability of A being true or B is true is equal to a certain number, here call it W, A or B, if you tell me that, you are actually not telling me anything about the marginals. You are just telling me something about this OR. And with the Credal version, I can take a circuit and I can put that weight there for the A or B without having to specify the weights for each one of the 3 atoms that satisfy that, the configurations that satisfy that. I can leave that as a Credal set. I can leave that unspecified as a set, and I can do inferences later on. So that's the key, or why the Credal version can help us so much on putting probabilistic propositional logic into these deep models. And then we can discuss further if you are very interested on the topic. I think there is lots going on at the moment on trying to mix those two. So this is my talk. I think I'm on time. So the joke about being late is a bit wrong, but thank you.
Questions?
So I have a question. So if I remember correctly from a very long time ago, when people started doing probabilistic logic, so Nilsson, Helper, and Bacchus, they considered probability statements of the one on your previous slide, right? They said the probability of certain events is some number, and then they were all studying, the satisfiability of these constraints. Is the Credal set empty or not, right? And so have you studied these connections between kind of the 35-year-old probabilistic logic literature and Credal sets? Because I think it's very related.
Yeah, it is. Thanks for the question. Yeah, it's indeed very related. Just checking if the Credal set is going to be empty or not, in general, it's going to be a hard task. But the circuits come to save us in that. So I think that there are a few combinations of things that we didn't have at that point. One of them is this probabilistic circuit, where you can do inferences efficiently. And for instance, queries on the circuit, like, is this empty or not, you can do efficiently. So if you have a Bayesian network, then you have the problem of what is the complexity of the inferences you're going to run on this, including the complexity of the inference. Is this empty or not? The circuits come to save us on that side. So I would say we have more material now to work than we had at that time. The second point, maybe I don't want to go too philosophical on that, but there is quite a big difference if we say, what's the probability of this variable given a certain logic formula, and what's the probability of this variable given that the probability of this logic formula is 1 even. Even those two things are yield different results. And I think that this is another thing that we couldn't process before. So in the first case, if you do that, you are actually updating. When you update, you end up not answering the same as you would without updating. And the second, you're not doing updating, you're just putting a constraint inside. And I think 30, 40 years, we didn't have computational power to handle those things. But many of the ideas are the same as there, I would say. In some sense, we are bringing back some of those ideas with tools that we have now. That's how I would interpret that.
Yeah, I think it's worth investigating that connection, because at the time it was really just a logic, right? Like you made statements in a logic about the probability of certain events and they're conditional, and then it was really the SAT problem in the sense of, does there exist such a distribution that has these properties, and then when is it decidable, what is the complexity, and so on.
Yes,
yeah.
All those questions are still the same, right? The difference is to be able to use like circuits to, well, basically we are restricting, another way of telling it the same, is that we are restricting the models that we work with models that are efficient to do the computation. Because obviously if we don't, then the thing is hard. There's nothing to do about.
Yeah, you just answered the question that I wanted to ask, because there is a caveat when we say, oh, circuits are very efficient. They're efficient because you force them to be small. So if you start from an arbitrary Bayesian network and convert it to a circuit, sometimes it will be small, and then sometimes it will not be small. It will be still exponential. So I think that's an important point, but we should remember it.
Yeah, thank you for the comment indeed. And one of the reasons to try to work with circuits directly, or at least one of the justifications, was to say I fix the size of the model, so in whatever I want in terms of complexity, and then it's fast because I fixed the size, right? Which is something we cannot do with compilation unless we fix some characteristics of the Bayesian network to start with, like we do the learning with a bounded tree width or some other characteristic that would make the translation efficient. So indeed, thanks.
All right. If there's no further questions, actually, we still have 10 minutes before the reception start. And as you may have noticed in the schedule, there's some time for discussion the next few days where hopefully we can do some whiteboarding and solve some open problems. And so Cassio was eager to share with us an open problem about the complexity of marginal map on tree-shaped graphical models, which is a much simpler problem than anything involving Credal sets. So this might be something you can solve here this week.
Okay, so let me change the hat. I don't care about Credal sets anymore. And I will talk to you about a very simple problem that maybe you do have the solution and I don't, but I do not know. So if you do, then please tell me. And if you do not have the solution, but you are interested, I'm very happy to talk about. Because I started looking to the problem way too long ago. That is 20 plus years. And I still do not know the solution of this one. And it's too simple as a problem. So I'm hoping you do have the solution. So the example is here. So let's say you have a collection of Boolean variables. And you have a collection of functions of 2 Boolean variables to non-negative integers. In this case here, say FAB, FAC, CD, and so on. Those are Boolean variables, okay? So you can look to each one of those functions as just a mapping returning you 4 numbers for each one of the 4 configurations of those 2, okay? Those are the functions. There is a restriction here, is that the underlying graph has no cycle. So if you write down an edge every time you have a function between 2 of those Boolean functions, you dot the graph, no cycles, okay? Now, the question is, I want to choose the values of the leaf nodes to maximize the product of those functions. So in this example, I want to choose the values of B, E, and F to maximize the product of all the functions that are defined here in the domain. That's it. That's my problem.
Over ACD.
Are you summing over ACD?
Oh, I missed the sum in the slide. Sorry, I did the slide a few minutes ago. I'm summing over the others. Yes, yes. So I will not dare to change the slide now, but I have pen. So of course. So I'm summing over the variables that are not in orange here, and that is the function that is there.
I think it was proved to be NP-half, no?
It is. So I do have a table somewhere. So there are a few different configurations there, but basically if you go beyond Boolean or if you make this the graph more complex, then you get a different kind of beast on your zoo. Most of them are NP complete, but sometimes it goes to NP with a PP oracle. If you have a general Bayesian network, it gets to weird configurations depending on the type of sum you put here. But I want to concentrate on the simplest of all of those, which is the case where they are all Boolean and there is no cycle here. So this case, I do not know the answer. If you give me the option of using one ternary variable, I can show it's NP hard. But if you give me all Boolean ones, I do not know. If you give me the opportunity to do, if you say that you are doing the minimization instead of maximization of this, I also can show you is NP hard. But the maximization I can't. Or maybe you, I don't know about, but I was not able to make this proof. And then I went to code because I said, if I don't know how to do it, I code. So I wrote a quite efficient algorithm to solve this. It's based on keeping a Pareto dominance for when you propagate these values. And then I've run experiments with different type of structures in the graph. And I did both for the minimum and for the maximum. Max value is a range for the output of the function. Nodes is the number of nodes. They are all binary. And if you take a look on this table, for the minimization version, the top there is with a particular structure, but random parameters. The problem seems to get harder as I increase the number of nodes. For the maximization, it didn't. If I encode the partition problem into the minimization version, because I can prove it's NP hard by a reduction from partition, it obviously grows. I'm not surprised by that. I cannot do the same because I don't have obviously I don't have a reduction to the other, otherwise I would tell you it's NP hard. But if you take random structures with random parameters, the minimization again starts to grow as you grow the number of nodes, while the maximization doesn't. So there is some sort of lack of symmetry on the max and the min. And it's a very, very particular case of this. So Rina is completely right. This is closed for almost every case. I would even dare to say I'm not sure if anybody cares about this case, but I don't know the answer. So
you showed that the map is already hard for naive Bayes, right?
yes.
So can we just like simulate naive Bayes by just having like a...
But I need more than binary. I need more than binary in that proof.
But you need a ternary variable, right?
Yes.
So two binaries, you encode the ternary, and you just reject the last value.
Then it's not a tree anymore to do that, because you have to connect those two to everything else.
Can't I emulate like exponential many states with just like picking one?
No, because it's a tree.
But you just need two nodes, right? And they're already connected.
Yeah, but you have to connect the others to the two nodes.
Don't solve it already. This is for tomorrow.
Right.
Tomorrow at 3:30 we solve this
But
problem.
But I like the discussion anyway. I think it's a simple enough problem, and maybe you do have a solution, and I would be very happy to hear about. I do not know.
Okay, so thanks again, Cassio. And